Welcome to APCV 320, Computational Thinking and Doing. This week's topic is Thinking Object-Oriented. Lecture slides were adopted from Professor Henry Wirshan, Applied Computing and Computer Science Program Director, who taught this class during the fall semester of 2020. In this voice thread, we are going to study object-oriented programming paradigm and how language influences our thinking process. We will study the fundamental principles of object-oriented programming. Object-oriented programming features were invented in 1960s, and the programming paradigm started to draw attention of the computing public at large in 1980s. Since then, object-oriented programming has become the most dominant programming paradigm in software industry. During the course of this briefing, we will present two contradictory viewpoints. Contradictory yet also complementary. That object-oriented programming is revolutionary and the other viewpoint that is evolutionary. Both in fact are true. So why has object-oriented programming remained popular for so long time? There are several reasons. It has a proven record of success. A lot of software products are created based on object-oriented programming and design, and the programming paradigm is able to scale well from the most trivial problems to the most complex tasks. Object-oriented programming provides a form of abstraction that's able to resonate similar techniques for people to think about problems in their everyday life. There are a lot of tools and libraries available in most popular programming languages such as Python to help software engineers and software developers build software products and design systems. For example, Python has been used by both good and bad hackers. The language also has been used by data scientists to analyze and visualize data. However, object-oriented programming cannot solve everything. It's not a panacea. In order to become perfectly skilled in programming, it still requires a lot of practice, creativity, persistence, logic, and the ability to build and use abstractions and experience. In linguistics, there are studies emphasizing the fact that the languages people speak will affect the way they view the world around them. So take the definition of the term paradigm. It is 1. A list of the inflectional forms of a word taken as illustrative example of the conjugation or declension to which it belongs. 2. An example or model. We will review this further. In the Eskimo-Inuit languages, there are a large number of words describing snow. Similarly, in the Arabic languages, there are many words describing camels. It's true that a community where people share common interests intended to build a specific vocabulary with which people can discuss concepts within the community. What happens in natural languages actually is also true in programming languages. When a software developer approaches a problem in a specific programming language, the language the software developer uses is able to affect how the software developer approaches the problem. So the algorithm used to approach the problem is indeed impacted by the programming language used by the software developer. How does the language we use when approaching a problem impact the solution that we use to solve the problem? We like to use an example problem to demonstrate this. The example problem has a long sequence of DNA values. A value is an integer value. The long sequence has a large number of values. The order of the number of values on the sequence is on the order of tens of thousands. So this sequence is very, very long. The problem is to find the repeated sequence of m values from the sequence of DNA values. The m number here is very small. It could be 5 or 10. In order to approach a problem, the first student wrote a Fortran program. Fortran is a popular programming language used for scientific research applications. It's kind of natural to use a program in Fortran to approach this problem. However, after the student wrote this program, he found that executing the program to discover the pattern actually takes a long time to solve this problem. So this slide shows another solution in APL programming language, a solution written by a friend of the student. In the APL programming language, the friend rearranged the DNA data into a list of small sequences. Each small sequence is composed of M values. The M values actually are adjacent to each other on the original DNA sequence. For example, the first sequence is composed of the values between positions 1 to M on the long DNA sequence. The second sequence is composed of the M values between positions 2 to M plus 1 on the long DNA sequence. The last sequence is composed of the last M values on the long sequence of DNA values. After the data arrangement, the APL program written by the friend sorts the list of small sequences using the APL sorting operation. The sort operation is able to rearrange the sequences on the list, and the sequences who have similar DNA values can be arranged close to each other. After the sorting operation, the APL program continually compares adjacent sequences. If there exist adjacent sequences of DNA values equivalent to each other, the APL program is able to find these repeated M values on the original sequence of the DNA. It turned out that the APL program is able to solve the problem faster than the Fortran program we just started on the original slide. Note that the APL programming language is interpretation-based programming language, and the Fortran, on the other hand, is a compiled programming language. Fortran has been good at scientific applications. Usually, Fortran programs can run faster and more efficient than APL programs. So why is the APL programmer able to find a better solution for this particular problem? The reason is that Fortran is used to loop statements. It's a simple program to solve a scientific researcher problems. On the other hand, sorting is a built-in operation in APL programming language. Good programmers in APL tend to find the creative uses of sorting operations. The fundamental point here is that the languages we use when approaching problems are able to impact how we approach the problems using certain algorithms. In linguistics, there is the Sapir-Whorf hypothesis that asserts it may be possible for an individual to work in one language to express thoughts and ideas that cannot be translated or even understood in a different linguistic framework. In computation, it's interesting to compare this possibility with almost the opposite concept, Church's conjecture. By nature, the conjecture must remain unproven. Acceptance of Church's conjecture has an important and profound implication for the study of programming languages. All general programming languages such as C, Java, and Python are Turing complete, which means that they are sufficiently powerful to perform any reliable algorithm, and any reliable algorithm is able to be performed in any language and it can be expressed in another language as long as the two languages can both emulate a Turing computer. Turing machines, first described by Alan Turing in 1936, are simple abstract computational devices intended to help investigate the extent and limitations of what can be computed. But certain techniques, such as object-oriented programming, do make it easier and more natural to address problems. A programming paradigm is a way of conceptualizing what it means to perform a computation and how tasks can be carried out and how they should be structured and organized. Imperative programming, which we addressed earlier in this class, is the traditional model of computation. This programming paradigm focuses on states of running programs determined by values assigned to variables during execution, and how execution flows are directed by the various statements, including loops and selections in programs. The imperative programming paradigm has a connection to the underlying of one computer architecture that's composed of a process unit and the memory component. The process unit acts upon memory, and sometimes the traditional computer programming paradigm is called the pigeonhole model of computation. In object-oriented programming, we do not focus on variables, statements, and flow controls, etc. Instead, we construct objects and classes, and we build the programs out of the little computing agents in communities. The top part of this slide represents the basic characteristics of object-oriented programming proposed by Alan Kay. We will talk about the fundamental principles one by one in the following slides. Before we have a closer look at the basic principles, I'd like to review a scenario which is presently in the textbook recommended to you by Timothy Budd. So, in this scenario, I will order some flowers for my friend who lives in another city, and I'm ordering the flowers at a flower store. In the flower store, there is a florist who is taking care of my order. In addition to Chris and Fred, there are other agents who are also involved in the task, including the florist who lives in my friend's city, the bus driver who will send the flowers to my friend, and all the agents must work together and collaborate to accomplish this task, and each agent in this narrow place plays a certain role and provides some service in order to resolve the problem. The mechanism that was used to solve this problem was to find an appropriate agent, i.e. Fred, and to pass to this agent a message containing a request. It's the responsibility of Fred to satisfy the request. There is some method used by Fred to do this. Chris does not need to know the particular method that Fred will use to satisfy the request. Indeed, often the person making the request does not want to know the details. This information is usually hidden from inspection. The first principle in object-oriented programming is everything is an object. Actions in object-oriented programming are performed by agents. They are also called instances or objects. And in the scenario I just described, there are many agents, objects working together, including myself, my friend, the florist in my friend's city, the driver, etc. Every agent or object has a part to play, and the result is produced when all agents work together to solve a problem. The second principle of object-oriented programming is objects perform computation by making requests of each other through the passing of messages. So actions in object-oriented programming are performed by objects, and they are produced in response to requests for actions and encode the messages. Instance object may accept a message, and the intent in response to the message, the object will perform an action and return a value if necessary. And to begin the process of sending flowers in the scenario we just studied, I give a message to the florist in the flower store. And she in turn gives a message to the florist in my friend's city, and she and the florist in my friend's city gives another message to the driver, and etc. etc. And you can see how messages are passed among the agents in order to perform that task. Object-oriented programming provides an abstraction to hide unnecessary detailed information from clients and users. For example, in the scenario we are studying, and I'm using the service provided by the flower store to send the flowers to my friend, I don't need to know how the flowers will be sent to my friend's place. I just need to make sure the order is sent. I just need to make the order by letting the florist in the store to know the following: what is my order, and what flowers I want to send to my friend, and what is my friend's address. In object-oriented programming, each message is sent to an object which is called a receiver object. So that is, a message is always associated with the receiver object, and the receiver object is able to perform actions in response to the message that is sent to it. So note that the same message might be able to be received by different kinds of receivers, and the interpretation of the message may be different depending on the receiver who receives the particular message. So this slide shows some supplementary information regarding different receivers and how they react to the same message sent to them. So for example, we have a Fred who is a florist, Elizabeth who is a wife, and Ken who is a dentist. The same message to send the flowers is sent to Fred, and the message intended to let the receiver to send your flowers to my friend. Fred is a florist, and he probably will be able to act upon the message to accomplish the task. Elizabeth, the wife, may also know how to send the flowers to my friend. The last agent, Ken, who is a dentist and probably doesn't know how to send the flowers to my friend. Well, certainly the three receivers will act upon the same message, but their behaviors and actions probably will be different from each other. In object-oriented programming, the same message could be sent to different types of receiver objects, and the behaviors of the receiver objects are determined by the types of receiver objects. For example, as we previously saw, a florist's behavior is different from a housewife's behavior. even though they both act upon the same message, just send the flowers to my friend. In object-oriented programming, one of the principles is every object has its own memory, which consists of other objects. I would like to remind you of some data structures we learned before in Python. For example, a list in Python is an object, and the object has some memory to store every element on the list to do the structures, and the list could contain some other objects. For example, if a list has a string, the string object is contained in the list object, and also the list could contain some sublist, and the sublist object is also part of the list object's memory. Each agent in object-oriented programming is like a miniature computer. The agent is able to perform a certain task. It's also important to know that objects in object-oriented programming are allowed to perform their tasks without unnecessary interactions or interference with other objects. This is similar to the real-world scenario. For example, when the driver is asked to send the flowers to a certain address, the driver doesn't need to know some information regarding how he should drive to that address. We choose which route is the best route between the starting location to the destination location. Every object in object-oriented programming is an instance of a class, and the class groups of similar objects. The class is a repository for behavior associated with an object and the behavior. For example, I expect from the florist at the particular flower store I'm making the order to send the flowers to my friend is based on some general idea I can expect from florists. So the florist at the particular flower store is just an instance of the class of a florist. Behavior in object-oriented programming is associated with the classes and not with individual instances. For example, in Python, we have used list instances, and all list instances actually behave similarly, and the behavior is determined by the list class defined in Python. And all list instances able to act upon some messages such as sort, and you can send the sort message to list the instance in response to the message, and the list if the list object is able to sort the list of the elements on the list. Classes in object-oriented programming can be organized into a hierarchical structure. So just like in our scenario, a florist is a shopkeeper, and a shopkeeper is a human is a mammal, etc. So the classes including a florist, shopkeeper, and the human in this scenario could be organized into a hierarchical structure. You can map the instance of a florist all the way up the tree to mammal, animal, living object, and finally material object. One of the fundamental principles proposed by Alan Kay is that classes are organized into a single root tree structure called an inheritance hierarchy. So information associated with one level of abstraction in a class hierarchy is automatically applicable to the lower levels of classes within the same hierarchy. This principle is applied in some programming languages. For example, in Java, the root class for all classes defined in Java is actually an object, and the methods defined in object class are able to be inherited to all the classes defined in Java programming language. However, this principle is not applicable to every programming language. For example, in Python, we are able to define a subclass extending from multiple classes. So this is the class hierarchy in Python is not a single root to the tree structure. The view of a programming represented by example of sending flowers to a friend is very different from the conventional conception of a computer. The traditional model describing the behavior of a computer executing a program is a process state or pigeonhole model. In this view, the computer is a data manager following some pattern of instructions, wandering through memory, pulling values out of various slots, transforming them in some manner, and pushing the results back into other slots. By examining the values in the slots, one can determine the state of the machine or the results produced by a computation. Although this model may be a more or less accurate picture of what takes place inside a computer, it does little to help us understand how to solve a problem using the computer, and it's certainly not the way most people go about solving problems. In contrast, in the object-oriented framework, we never mention memory address, variables, assignments, or any of the conventional programming terms. Instead, we speak of objects, messages, and responsibility for some actions. An easily overlooked benefit to the use of object-oriented techniques is the power of metaphor. When the programmers think about problems in terms of behaviors and responsibilities of objects, they bring with them a wealth of intuition, ideas, and understanding from their everyday experience. When envisioned as pigeonholes, mailboxes, or slots containing values, there is little in the programmer's background to provide insight into how problems should be structured. Journalists make use of metaphor every day, as in the following description of object-oriented programming from Newsweek. It says, unlike the usual programming method, writing software one line at a time, next, object-oriented system offers larger building blocks that developers can quickly assemble the way a kid builds faces on Mr. Potato Head. Possibly this feature, more than any other, is responsible for the frequent observation that it's sometimes easier to teach object-oriented programming concepts to computer novices than to computer professionals. Novice users quickly adapt the metaphors with which they are already comfortable from their everyday life, whereas seasoned computer professionals can be blinded by an adherence to more traditional ways of viewing computation. Object-oriented programming is not simply features added to a programming language, it is a new way of thinking. Object-oriented programming views a program as a community of agents termed objects. Each object is responsible for a specific task. An object is an encapsulation of state, data values, and behavior, which is operations. The behavior of object is dictated by the object class. An object will exhibit its behavior by invoking a method, similar to executing a procedure in response to a message. Objects and classes extend the concept of abstract data types by adding the notion of inheritance. Inheritance is the mechanism of basing an object or a class upon another object or a class, retaining similar implementation. So that was rather a short lecture. If you have any questions, please feel free to email me. And in Module 9, we will discuss abstraction and object-oriented in Python.